Hello.
Yes, sir.
Am I audible?
Yes,
Yes,
sir.
sir.
Yes, right. Okay. Okay. Had dinner?
Yes, sir.
Okay. So what else? Python going on, right?
Pardon me?
Python session is going on, right?
I don't know actually.
Yes, sir.
Okay. So I will take session is scheduled for 2 hours, but maybe I will take 1.5 hour, not more than that. Okay. So even you should have enough sleep and everything, right? We strive for only two things in life, right? Proper sleep and proper food.
Yes, sir.
So I don't want to take out those things from you. So I will finish it quick. So let's wait for 1 more minute and we will start discussing. And whatever we discussed yesterday, that null and whatever the question, AQ 11.1 question number 1. So that should be option 2 only. Okay. So
Okay.
inform for the rest of the people. So we have been confusing between option 2 and option 3. Why option 3 is given correct and it should be option 2, right? It is option 2.
So whatever we discussed actually yesterday was right. No, and that means
Yeah, yesterday whatever we discussed is correct. So null
Okay.
hypothesis is basically the claim. So whatever the claim or whatever we are trying to verify should be the null.
Okay.
Okay, is my screen visible?
Yes, sir.
So whatever the null hypothesis is, usually we try to verify this null.
Right.
So we are trying to verify this null, and whatever the alternative is, just the opposite of this.
Right.
Okay.
Yeah.
So that is how it will be. So I will just wait for one minute or two.
Sure, sir.
Okay. Then we will start. So I can see you, Ganga, Prasad, yeah, Ayush, Krishna Mohan, Daniel, Harishankar, Kavita, Nikhil ji, Pavan. So there is other guy called Binayak Basu, right? Binayak Basu. Basu. Am I audible clearly? Like, is my voice very low?
No, sir,
I-
clearly, sir.
It's clear. Yeah. It's clear.
Clear,
Good
right?
night.
Yeah, very clear.
Okay. Okay, let me say it again. Whatever we discussed yesterday is correct. So the take you 11.1 question 1. So the correct option is option B. So correct option is B. So it is given as C, but we will change it to B. So basically null hypothesis is what we are trying to verify. So if there is a claim and whatever we are trying to verify is what the null hypothesis is. We verify against an alternative hypothesis, which is the complement of this claim. Okay. So alternative we will fix depending upon this null. Okay. Yeah. So I will quickly brief what we did yesterday. So we have seen. Yeah. Hello. So I request everyone to be on mute so that if you have doubt, please unmute and ask. So at any point, if you have doubt, you can ask me. Okay. So let me brief what we did yesterday. So if we have some samples taken out from one distribution and
That's is every month the same.
What is this? Every month? Okay. So we will fix some null hypothesis and we will fix some alternative hypothesis depending upon the claim we have, and we are going to test that claim. So in order to test that claim, we define a test by considering an acceptance set. So I guess everyone know what is an acceptance set now. So we will define one acceptance set. Depending on that acceptance set, we will define our test. And if our samples x1, x2, xn falls in this acceptance set A, we will accept H0. If my sample doesn't fall in this acceptance set A, then I will reject H0. So we will reject H0 and accept HA alternative. So we say that the claim is not legitimate. So whatever the claim is, we reject the claim. And in order to do this test and how to select this acceptance set, better acceptance set, we need to look at two types of errors possible, which is type 1 error and type 2 error. Type 1 error is basically when the null hypothesis is true, we reject null. So we happen to reject null when it is actually true. So this is what type 1 error is. And the type 2 error is the other case. When alternative is true, we end up accepting null. So these are the two possible errors. So yeah, these are the two possible errors, and these are called as type 1 error and type 2 error. And there are two metrics to define for every acceptance set. There are two metrics. Depending upon those metrics, we actually decide which one is better acceptance set. So each and every acceptance set has two assigned values, which are significance level and power. So each acceptance set has a test, equivalent test, and each test has two metrics: significance level or size of a test and a power of a test. Size of a test can be computed using probability of type 1 error, probability of chance of happening this type 1 error. So that is what significance level is. And power is actually equal to 1 minus beta, where beta is actually probability of type 2 error. That means what chance we can have type 2 error. So these are the two types of errors. And what we do is, our main goal is to make alpha and beta as low as possible for better acceptance set. So by taking different acceptance sets, we compute alpha and beta, and by comparing alpha and beta, we will actually decide which one is a better acceptance set. So this is what we did yesterday.
So size is the same as powers, is it, sir?
No. Size is this. Size is alpha.
Significant. Oh, significant.
Yeah. Size is significance level, and power is 1 minus beta.
Okay.
Yeah. Now what we will do is,
Sir, sorry to interrupt you in the middle. Today we are discussing about week 11 or week 10, sir?
Week 11. Is there anything to discuss from week 10? Are you
One
guys
second,
struggling
sir.
with
One
week
second,
10?
sir. Just hold on. I'll just increase the volume of my laptop. Yes, sir. Can you please tell, sir?
Okay, what am I telling is week 10 is actually only one thing, right? Only one count.
Yeah. That is prior estimation.
Yeah, prior. We will give you the prior. You see the samples.
Yeah.
Taking prior and samples into the consideration, you compute the posterior.
Yeah.
This is what we do in the whole week. So only one concept will be dealt throughout the week.
Okay.
So is there any? Are you facing any difficulty in solving?
No, sir. Actually, I have done only 2 lectures of week 10.
Okay.
So I'll just go through that.
Yeah, please.
Before solving.
And yeah, you can go to week 10 week 10, but there is no connection with week 11 and week 10.
Okay, sir, I joined just now, sir. Could you please help me in revising from the first, sir, please?
Revising in the first?
Under the previous one, hypothesis, what you started from the beginning, because I was not there. Just now I joined, actually.
Even I can again visit that, but the problem is I should complete many topics, okay?
No,
you
sir.
Just open the YouTube, okay? Just open the YouTube. 5 minutes, like just backwards from 5 minutes. I just explained it, okay? Quickly you see there, just come back. If you don't understand anything there, Just come back and we will discuss here. Okay.
Okay, sir. Okay.
So yeah, we will solve some problems on size and power. Okay. So these are the problems in the lecture 2. So let me take the first problem, which is, let us say our null hypothesis is saying that the coin is unbiased. Okay, let me change the color. So, and the alternative we have taken it as biased coin. Okay, unbiased means probability of head is 0.5 and probability of tail is 0.5. So now what we are doing is, unlike yesterday we did only 4 tosses, but today what I am doing is, with 4 tosses, guessing whether it is unbiased or biased is a very illogical thing. So what I did is, now I am tossing the coin 100 times. And by tossing the coin 100 times, what am I noting is, I am noting the number of heads. So how many number of heads I am seeing when I toss the coin 100 times. So this will be a number. So this t is a number now. And what is the range of t? So this is a random variable. And what is the range of t I can have?
0 to 100. Sir.
Range of t is 0 to
100.
100. Correct. So I am tossing the coin 100 times. So I can have maximum of 100 heads and a minimum of 0 heads. So this is the range of t. And when I toss the coin 100 times, so one sample, I will have one particular number for t. Is that correct? So when I toss the coin 100 times and when I count how many number of heads are there, so that is the static value.
Yes.
Yes, sir.
Okay. Now, yeah, as that is a static value, this particular t in our hypothesis testing is called test statistic. So where we use this static value to compute the test. So we actually do the testing based on the static value. So whether the static value is within our range or outside the range, and looking at that, we decide whether to accept H0 or to reject H0. So this particular t is called a static test statistic. So this can be anything. See, here we have taken number of heads, or I can take the mean. Test statistic can be samples, sum over the samples divided by n, or it can be variance. So test statistic can be anything. You define the test statistic. Depending upon the test statistic, we define a test, and by performing the test, we actually decide whether to reject H0 or to accept H0. Clear?
Basically, sir, test statistic is it the random variable which you consider for creating the test, right?
Creating the test. And what
Okay.
happens is, ultimately it becomes a static value.
Right.
Random variable. When you compute the samples, when you have the samples, it is actually a static value. You can
Right.
compute the value exactly. So that is what we use. So see here, what I did is,
It is a function of sample, right?
it is a function of samples. Correct. So now what I did is, I defined a test statistic, and also I defined an acceptance set. So this also we should define, right? Acceptance set is also we have to define for a problem. So the acceptance set is when this p value is less than or equal to some c. Okay. So in yesterday case, if you remember, we have said 4 times toss, and I have taken one acceptance set as if my number of heads are less than or equal to 2. Remember? So I said one acceptance set as I will accept only, so I will accept H0 only if the number of heads I see is equal to 2 or less than or equal to 2. How many of you remember this?
Yes, sir.
Yes, sir, yes.
Yes, right? So
We
here
calculated
also when I toss a coin 100 times, my acceptance set, how I will keep my acceptance set is, if the number of heads I see, if it is less than or equal to some value, c is any number, so I can keep it 50 or I can keep it 60. So if I see the number of heads as less than or equal to 50, so if I see 40 heads or 30 heads or 50 heads, what will I do? what will I do now? So I have tossed the coin 100 times. I have seen only 50 times heads. So what how will my mind,
We'll think that it's unbiased coin, no?
we think that it is an unbiased coin. That means what we are doing, we are accepting H naught. Correct?
Right.
Yes, sir.
So if it is less than or equal to some value, so if it is greater than some value, maybe I can keep it like 55 as my threshold. So T can take any value in between 0 to 100, but I kept the number of heads. If it crosses 55, then I think it's like something like a bias towards heads, and I say I will reject H naught and I will accept the alternative. Correct? That is what we do. If we observe some
Yes,
70
sir.
heads,
Right, sir.
70 heads, if you observe
Yes.
some 70 heads, what will we think? We think that this is an biased coin where it is biased towards heads. Correct? That is what alternative is. So what we do is, this is not an unbiased coin. We reject null and we accept alternative. So that is what. So instead of 55, we kept some value as C. So now our acceptance set is less than C. So this is what our acceptance set is. So if it is from 0 to C, we will accept it. And if it is greater than C, we will reject it. That is what the test will be. So what is the test now? We reject H naught. This is accept H naught. And this is the region where we reject H naught. Okay. So depending upon this test statistic, so if your T is something less than T, less than C, so we will accept H naught. Correct?
Yes,
So if
sir.
I replace this C with 55, okay, and I got T as, when I toss the coin, I got T as something like 50. So T value is 50 maybe. Okay.
Accept.
Will I accept or reject?
Accept.
Accept. So my T will be here. If T is 50, my T will be somewhere in the acceptance region. So I will accept. That means I say this is an unbiased coin. When my T is something like 60 or 65,
Reject.
it's in the rejection region. So T is equals to 65 means what it means? The number of heads I have seen is 65 heads I have seen out of 100 tosses. Correct? I will reject H naught. So this is what you have to do. First and foremost thing, when you solve a problem, you should identify what is the acceptance region, what is the rejection region. Okay. So instead of 55, you have C. That's it. So we are going to find the value of C, the best value for C. So the good acceptance set we have to find. So in order to find that, what we have to do, we have to find size and power of the test. Okay. So how do we find that? So we know alpha is probability of type 1 error. So what is type 1 error? You reject H naught when
It's not, it's true.
Yeah.
H naught
It's true.
true. Correct. And what is rejection region? So if this is A, now this is A. So what is this?
Greater than C, greater than.
Greater than C.
Greater than 55. Greater than
Mark
C.
it in the sets. So if this set is A, so this is a set, right? Acceptance set A. A is a set.
A complement.
Yeah. So rejection region is A complement set. Correct? So reject H naught means it's like A complement. So we want the probability of A complement event A complement, when we know that probability of heads is 0.5. Okay. Now tell me, what will be this equal to?
If it is okay, can I ask you to repeat the last bit that you just said about the A complement?
Yeah. See, this is the full set I have.
Correct.
Correct.
Yes.
And out
Yes.
of this full set, from 0 to C is
C, acceptance criteria.
So see, this set I can explicitly write like this 0, 1, 2 to C.
Yeah.
Correct? So
Yeah.
less than or equal to C is what? T range is from 0 to 100.
Acceptance range is from 0 to C.
Acceptance region is 0 to C.
Yeah.
Correct?
Yeah.
And when will we reject H0?
If it is anything more than C.
Yeah, anything more than C.
Yeah.
And what is that set will be? Anything more than C is like C plus 1, C plus 2, and so on till 100.
Till 100. Yes.
So if this is A, if this set is A,
Yeah.
and the universal set we have is from
Yeah.
0 to
Okay.
100.
A's complement. Okay.
What is this?
A's complement.
A complement.
Hmm.
So when are you going to reject H0?
When it is
your,
an A complement. Yeah.
when your T is in A complement.
Correct.
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 So we need to find the probability of A complement events.
Yeah. A complement events given P of H is equal to
Probability
0.
of heads is 0.5. So how many possible values are there? So probability that T can be equal to C plus 1.
100 minus C. 100 minus C.
C plus 2, like this, probability that T is equal to 100. Correct?
Yeah.
These are the possible events. And what is the probability that getting C plus 1 heads out of 100 heads?
Yes. Probability of getting C plus 100 heads. Okay.
Is this correct?
Yes.
So T is equal to C plus 1 is what? Number of heads are C plus 1. And you are tossing the coin 100 times. What is the probability that you get C plus 1 heads when you toss coin 100 times? It will be 100 C plus 1 times probability of getting heads to the power C plus 1 times probability of tails to the power 100 minus C plus 1. Is this correct?
Yes, 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 yes.
Yes, sir.
Yes,
Yes,
sir.
sir.
This is something like binomial.
Binomial. Sir.
Correct. So what is the second probability of getting C plus 2 heads?
Yes.
100 cc plus 2.
100 to C plus 2, 0.5 raised to C plus 2 into 100 minus 0.5 raised to 100 minus C plus 2. Sir.
Like this?
Yes,
like
sir.
this till 100. What is probability of getting 100 heads? 100 C
100 choose 100. Yeah, 0.1 by 0.5 raised to 100 to
whole to the
0.5
power
raised
0.
to 0. Yes, sir.
Correct. So can I write this whole bunch of values by using this summation symbol?
Yes, sir.
Yeah.
Where something like it is taken as
Equal
K
to C plus
C
1 up to
1
100.
and 100 Ck times 0.5 to the power K
K, yeah.
times 0.5 to the power
100 minus K.
100 minus K. Correct. So my alpha is this and it is dependent on C. Observe this. Depending on the value of C, my alpha value changes. If my C value is something like 50, so it starts from 51 to 100. If my C value is 60, it starts from 61 to 100. Correct? So if I increase my C value somewhere to 90, so when C value is 90, C value is 80, C value is 70, C value is 60, and C value is 50. Out of all these values, at which value alpha will be less?
90.
90. So for every C value, we will have alphas, right? So let me say
Yes,
alpha
sir.
1, alpha 2, alpha 3, alpha 4, alpha 5. These all are significance levels of for each value of C. Okay, out of all these alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, which value will be smaller? Think about this. It is not that difficult. Think about this. So alpha 1 is basically summation from 90.
That's equal to 90 only because it will be divided by 90 factorial. So maybe.
So this is something like 91 to 100. So you are going to take only 9 probabilities.
Should be
And what is
C is
alpha
equal to
2?
50.
Huh?
C is equal to 50.
No. See, what is alpha 2? Alpha 2 starts from 81 to 100. correct?
Yes.
So see, you see 81 to 100 is smaller or 91 to 100 is smaller?
91 to 100.
21 to 100 is.
See, here you will have 19 values.
But you are raising up to a higher number, right?
Hmm?
But the exponent, the index is higher, right?
So what? See, when you
Those are less than 1, no?
when you
one.
are summing up from 81 to 100, inside that there you will sum 91 to 100.
Okay, the base is less than 100. Okay.
So see, if you logically observe, when you are summing from 91 to 100 and when you are summing from 81 to 100, inside that there will be a 91 to 100 as well as 81 to 91. So this sum you can split it.
81 to 90.
So 81 to 90 plus 91 to 100. You can split this 81 to 100 sum as like this. And this is alpha 1. And alpha 1 say you are adding something to it. And this becomes alpha 2.
And so on.
And so on. When you start from 70, you are taking more and more values. Correct? From 70, it's like 71 to 100. So alpha 3 is basically summation from 71 to 80 plus alpha 2.
So, but if we see that way, it will be C99 will be the optimal value, no, in that case.
Only see for alpha. I'm
Okay.
for alpha.
He is asking which one will be smaller.
Okay.
Right.
So I just pick some values and I'm asking for which value of C alpha 1 gives you smaller.
90.
Right. We have to check beta as well. Okay, got it. Yeah.
Among this, it will give you 90.
Even sir, there is other logic also, sir. Like C stands for number of hits, right?
Yeah.
So probability of getting 90 hits out of 100 will always be less than probability of getting 80 hits. Will always be less than probability of getting 70 hits, like that.
Okay. Whichever you understand. Okay.
Yes, both are clear, sir.
Yeah. So now you understand what is the linking between C and alpha. So if I decrease C, if I increase C, my alpha value decreases. Correct? That is what happening, right? If I increase the value of C, my alpha value I can decrease. And I can take 99 or I can take 100 also. My alpha will be 0.
Yeah.
In effect, if the sum of the series is what you are actually talking.
That is what sum of the series. That is what alpha is.
Right.
Alpha is actually the probability of type 1 and we have computed the type 1 error only. This is what the type 1 error probability. And this is what alpha b, summation to C plus 1 to 100. Okay. Now what we understood here is if C increases, if I increase my C, my alpha value decreases. But this is not only the sufficient thing. I should also look for beta or I can look for power. So what is 1 minus beta?
That is power.
Yeah, it's
beta.
power.
Except at alternative hypothesis and when alternative hypothesis is true.
So reject H naught
when HA is true.
Okay. See, yesterday only we proved beta is actually probability that we accept H naught when HA is true.
Sir, this is the place where I was a bit confused, sir.
Yesterday we discussed, no? Like E of A given P.
Yes, sir, but here I actually get a note of it also. Can I ask a query?
Yeah.
So HA, see, when we are saying HA is true, when rejecting HO is there in the null hypothesis itself. When HA is true and you accept H naught.
Yeah.
But here reject H naught again, sir. So this is same.
1 minus beta. This is 1 minus beta.
No, that's okay, sir. That's okay. I'm talking about only the right side. 1 minus beta is okay. What I'm saying is this itself is misleading for me. For example, reject HO given HA is true. I mean, it doesn't make sense at all. I think why I'm saying that is anyway in the null hypothesis you are going to reject H naught when H naught is true. Here HA is true. So if HA is true, but you will have to accept H naught, only then it will become false, right? But here we are saying that if you are rejecting H naught, which means you are accepting HA.
I know. I understand what you are trying to say. So
Yes.
this is an error. So beta is an error, type 2 error. Okay. So this is an error,
Okay.
but this is not error. This is
Okay.
actually an event. So
Okay.
in how many cases you actually reject H naught
Mhm.
when really HA is true? Matlab, in how many cases you accept HA when HA is true?
So
So
if
We are
every time
not,
you don't accept,
let's
right?
we
say,
didn't got any error in how many cases?
Ah,
so if we let's say put only beta, in that case we can put accept H naught, right?
yeah.
Accept H naught when HA is true.
Hmm.
That will be beta.
That is error. So this is an error.
That's what I'm saying.
Ah,
Let's say for time being, I'm not putting 1 minus beta.
You
I'm just
can
putting.
compute beta, yeah.
So for beta, I can take it as property of accept H naught when HA is true.
Correct. And you
Okay.
just do final
Okay.
computation.
Okay.
You just 1 minus of it, that will give you the power.
Okay. So
Even
1 minus beta will translate to reject H naught.
reject H not given HA is true. So yeah. So what
But
this
that is actually the right scenario, isn't it? Rejecting H naught when HA is true is the right scenario.
is the right scenario, but how many times you are actually correct? 100% time you can't be correct, right? There is an error.
Mm-hmm.
Sometimes you make error. Removing that error, how much percentage we are actually correct is what this probability is. Okay. So that is why this is power. With how much power you can actually do the testing. So let's say 90%. That means you are correct. If I perform this test 10 times, you are actually correct 9 times. You can't be correct all the 10 times. So sometimes what you do is, even the alternative is true, you sometimes you accept H naught. For some samples you accept H naught, and that is an error. Correct? So when you make error, remove that error from the total number of cases you do. If you remove the error, how many times you are actually correct is what this probability is.
So we can also do this way, like while computing power, which is 1 minus beta, just compute beta and then subtract from 1. So
From
that,
1, that is also
okay.
So this is nothing but again when will we reject H naught when it falls in the A complement region, and HA is true means probability of head is 0.6. So the same thing we have summation K is equals to C plus 1 to 100, but here it will be 100 C plus 1. The probability of heads will change. Success is changed. It's like 0.6 to the power C plus 1 times 0.4 to the power
minus C plus 1.
Sorry, K 100 minus K. Okay. Now you observe, this is the power.
Now you lost something, sirs.
Are you speaking, sir?
ऐसा क्यों हो रहा है? आज तो मैं भी होस्ट नहीं हूँ।
Hello.
कल आप ही किक कर रहे थे सर को ना?
Hello.
Yes, sir. We are able to hear you.
Yeah. Sorry, man.
You are back now.
Sir, again Saurabh kicked you.
No, sir. Today I am not the host.
He is not the host. Host, if you are there, can you make me co-host? Okay. Okay, let me get the access meanwhile.
Sir, this was the first question that you were explaining. Like,
Problem 1 of week 2, lecture 2.
okay, because I was slightly late. Python class was going on.
Yeah. Is it not ended yet? It's not ended
I
yet.
don't think so because a lot of question was left. I left on the between. I just
No, just now it got closed.
okay.
Around 10:25 it got closed. Okay.
I left
So
on.
have you had your dinner
50.
then?
No.
Please have not then.
From 8, I am sitting on in front of my computer.
See, you can eat meanwhile, right? No,
Sir, I can't take a risk on the stats.
you can't take.
Risk
See,
for
एक साथ दो
stats.
काम नहीं कर पाओगे. खाना खाते ही can't you listen? Like I am just suggesting. It's up to you. I am not the one.
ठीक है sir.
खाली दिए शाम.
So okay, we are back. So this is the power of this test. So what should I do? Should my power should be higher or lower? So power is actually the how much percentage we are actually guessing it correct. How much probability?
Power should be higher.
It should be higher because
higher.
1
Power
minus
should be higher.
something. Yeah.
Yeah. So power should be higher. So what should be my C? Is it should be less or high?
Less.
Less,
In order to have more power,
It should be high, no?
Less.
Oh, sorry,
No,
less.
no,
less,
it should
less.
be low. It should
It should be low. It should be low.
Less.
Sorry,
you can
sorry.
again take the same.
Yeah, it should be low.
90,
Yeah.
70. So whenever this, if it is how much ever it is smaller, maybe 10 or so C is equals to 10. It's like summing over from 11 to 100. So it will have a lot more power, higher power.
Right.
So what happened here is C should be low in order to have my power high. So but above case we got C should be higher so that I will have a alpha value lower. So this like a cycle. Like when I increase C, my alpha will decrease, but my power will decrease. Power will also decrease, or beta will increase. When I talk about beta will also, when I decrease C, my beta will decrease. Okay. That means when I increase C, my alpha will decrease, but my beta increases. But when I decrease C, my beta will decrease, but my alpha will increase. So what should we do? So what should we do is we have to fix alpha. So usually we will fix alpha. So you fix alpha and find the least possible value for C. So this is what we are going to do. So what we are going to do, we are going to fix the significance level. So significance level is we are trying to minimize the type 1 error. Okay. So now how much type 1 error you can tolerate is in our hands. So if you are okay with tolerating of 5% error, so that means your alpha should be 0.05. Understood this? So
less than equals to 0.05, right?
So, yeah, if you are okay with probability of type 1 error to 5% or 0.05, that means you are saying that my alpha value can be 0.05.
So my error. Explain that bit about significance level you just said.
So this is the probability of type 1 error is nothing but the significance level.
Oh, okay.
So how much percentage or how much probability of type 1 error you can tolerate? It's up to us now. So if you are interested that okay, error can go maybe some 20% also, I don't mind. So then your alpha will be something around 20 by 100. So that means probability of type 1 error can be 20 by 100, which is 0.2. So you are okay with 0.2 also. So you are okay with 20% of chance of going wrong in type 1. So that is why we take alpha into our hands and we fix alpha. Once you fix alpha, what happens? So you know the alpha, then you can compute C. Correct?
Yes, sir.
Once you know alpha, you can compute C. So that is what we do. That is what we do in each and every problem from now on. So from 10.5, all the problems what we are going to do is we fix alpha and we compute the value of C, and that particular C is called as a critical value. So we will discuss those things also. But this is what we do.
Sir, can you scroll?
How to calculate P? Can you repeat once?
How to?
Like calculate P.
Calculate P.
You told us that we will find C and try to find P.
No, it's not try to find B. See, we will fix alpha and we will find the value of C, and sometimes we will not C. We will find C, and that particular C is called the critical value for this alpha. So we will discuss those things also now. I said we will discuss those things also.
Sir, can we go to 1 minus beta expression, sir? 1 minus beta expression.
Sir, how do you yourself fixing it as 0.05? Is it
that part? Yeah, we are fixing it. So
okay.
We are so it's up to now. It's up to us now.
Okay.
How much error we can tolerate? How much error you can tolerate? Like 5% error or 3% error or 2% error.
That level of error that I assume it.
Yeah, that is level error we will take, and corresponding to that level of error, we will calculate the C, and we call this particular C as the critical value. So beyond critical, you know the critical meaning, right? Beyond that critical level, we don't tolerate. We reject.
Danger will happen.
Yeah. So we reject.
Sir, 1 minus beta expression, sir, please. Just for 1 second.
So what are the 20 by 200?
Hundreds. Yeah.
See, this is nothing but we choose. So I said we can choose like 5% error or 20% error also. If you are not that much into error, even though if you go wrong also you don't mind, then you can tolerate for 20% error also. You take alpha value as 20. Your acceptance region will get larger. That's it. So how much tolerance you can accept, how much error you can accept is in our hands now. So that is why we fix alpha. So we try to fix alpha and find the value of C.
Sir, I was talking about that 1 minus beta, sir, just for 1 minute, sir.
See, 1 minus beta is actually...
Yeah, sir, here reject H naught we are writing, sir. In place of reject H naught, if we write, accept HA, condition on HA is true, will it be same thing or different thing, sir?
It is same thing, but we won't deal with alternative. We always deal with null. Okay. Either you accept null or reject null. So that is what either of it going to happen.
No, I think if we write accept H naught, condition on HA is true, that will become beta, right? Or that will still be 1 minus beta.
Accept H naught and HA is beta.
So if I write reject H naught is nothing but accept HA, right?
Accept HA.
So if I write accept HA, condition on HA is true. So the outcome will be 1 minus beta, or the outcome will be beta only?
1 minus beta only. Accept HA or reject H naught is same.
Okay, that's it. Thank you, sir.
Yeah. Okay. So this is what we are going to do. You fix alpha and find the least possible value for C. Okay. Let us move to the other problem. Previously, I had coin tossing 100 times. Now I have some random variable x which is coming from binomial 100 comma p.
Can I ask one question? Did we compute the alpha and 1 minus beta in the earlier problem, or we just leave it the formula?
If we compute alpha.
Did we compute alpha, or we just said that is equal to alpha? So we do substitution in the formula that we just wrote for alpha and then compute it, or how do we go about that?
That we will do. Okay. That is something like 10.5 lecture, right? So I'll go lecture by lecture. Okay. As of now, this is what we are going to do. We will do the later.
Okay. All right.
Yeah.
Thanks.
So now the problem is slightly changed, but the same problem. So the same setting. So if I toss 100 times a coin, with probability equal to 0.5, probability of success is equal to 0.5, same as x coming from binomial 100 comma p. So just correlate from there. Now my x is something coming from the distribution of binomial 100 comma p, where my null is p is equal to 0.5 and my alternative is p not equal to 0.5. Okay, and my test is I'm going to reject h0 if the difference between x and 50 is greater than 10. Okay, modulus difference. So that means either the left side of 50 or the right side of 50, I am allowed to use only 10 units. Okay, if it is more than that, I will reject h0. So now I will draw the straight line. Now tell me which one will be the acceptance region. So let's say this is from 0, some 10, 20, 30, 40, 50, 60, 70, 80,
So 40 to 60, no?
100. So
41 to 59.
If this is the test, what is the acceptance set?
0 to 40 and 60 to 100.
40 to 60 will be acceptance range, sir.
40,
Acceptance
40,
A will be
40 to 60.
So
41 to 41 to 59, sir.
41 to 59. Huh? So what is the complement of this? This will be my acceptance region. Less than or equal to?
Yeah, less than or equal to, yeah.
Correct.
Right.
So this is my acceptance region, and if I open the modulus, what will I get?
What is this equal to? Yeah, right.
Correct. So that means my acceptance region is this.
Yes.
Correct.
Yes.
So in this region, if my x value is in between this region, I will accept h0. Or what I will do, outside of this, I will reject h0. So in this or in this. So yesterday also I have told you two cases. One case is only two, if I toss coin 4 times, if I see only 2 heads, then only I will accept. If it is less than or greater than, I will reject null. So this is what here also the same setup. So within some region we are accepting, and left side of it and the right side of it we are going to reject it. Okay. So here I reject h0. Here also I will reject h0. If my x is from here 60 to 100 or 0 to 40, I am going to reject h0. If my x is in between 40 to 60 only, I will accept h0. Okay. So the graph is okay now.
Sir, come again with the graph once.
Yes.
Please.
So if I know the test, I know the corresponding acceptance set also, right? So each and every test will have a corresponding acceptance set.
Okay.
So you have to, once we have given you the test, you can actually derive the acceptance set. So I said if my x is modulus x minus 50 is greater than 10, I am going to reject h0. So can you identify what all x I am going to reject h0?
It's a complement of this test.
No. So what is this region?
This region.
So how to open this? So mod x minus 50 greater than 10.
Okay.
So this is something like x minus 50 less than minus 10 or x minus 50 greater than 10. So if I remove modulus, this is what it is going to be.
Okay. Okay. Yes, sir.
Is this correct?
Yeah. Yes.
Okay. So that means x less than 40 or x greater than 50. Correct?
I mute kar lo.
Yeah. So please be on mute when you are talking to someone. So when x is less than 40 and x is greater than 60, I am going to reject h0.
Okay.
Correct?
Okay. Yeah.
Now what is the acceptance? When will I accept h0?
When x is greater than 40,
greater than or equal
to 40 and x is lesser than or equal to 60.
So that is what it is. 40
yeah.
to 60.
Okay. Okay, sir.
So
Okay,
in this region, I will accept. and
Okay.
outside this region I will reject.
Okay.
Okay.
Okay,
Done?
sir. Done. Thank you, sir.
Now our question is we have to find alpha and beta. So alpha is probability that we reject H naught, which is, I am writing it directly, A complement. So this is the acceptance set. I am going to reject H naught. When will I reject H naught? In this region, A complement. And the probability P is 0.5. Correct? So what is the A complement region is? So it somewhat starts from 0 to 39 and from 61 to 100. Correct?
Yeah, right.
And this is like 100 CK 0.5 to the power K and 0.5 to the power K. Right? Correct? Sorry, 100 minus K. Am I correct? Did I lose
Yes,
the
sir.
connection again?
No, sir. You're audible.
Everyone are silent. I'm
No,
totally
no.
confused. Okay.
No. Okay.
I thought I lost the connection again.
Let's see.
Okay, is it difficult to understand how we got here?
No, sir. Actually, I'm writing side by side, so
Yeah.
it's taking time
That
to
part I
respond.
have not.
No,
Sir,
sir.
1 second, I have not understood that part, sir.
Which part?
That A complement condition
okay.
P equal to 0.5. You are writing K is equal to 0 to 39. That part I have not understood.
Okay, so we reject. So we know alpha, right? Alpha is nothing but probability of rejecting H naught.
Correct, sir.
When actually H naught is true. So
Yeah.
that means P is 0.5.
Yes, sir.
So when will you reject H naught? Whenever my X belonging to this A complement region, I will reject H naught.
Yes, sir.
So in this region, if my X falls, I will reject H naught.
Okay.
Correct?
Okay.
What is the probability of happening that my X actually takes in the A complement set? So that is what we are trying to get.
Okay, I understood.
So what is the probability from
that is
0
0
to 39
and 61 to 100.
to 100?
Yes.
100.
Yes,
So
yes.
getting 0 to 39, 100 CK, 0.5 to the power K times
N
40
minus
to the
K.
power
Yeah.
N minus K. And this is also the same thing, 100 CK, 0.5 to the power K and 0.5 to the power 100 minus K. So this is what alpha is, correct?
Yes.
What is beta now? So this will have a value, right? So there is no C here. So we have already given, there is no C here. So we can compute this. We can compute this. If you add this, that will be the value of alpha.
Right.
And what is power? Which is 1 minus beta, which is probability of reject H naught when alternative is true. Correct?
Yes, yeah.
The same thing. When are we going to reject? So it's like K is equal to 0 to 39.
So, but I'm having a query over here. Now, in this case, it's not 0.6, right? It's like not equal to 0.5. So, in that case, what will we
Okay. It's not equal to 0.5, right? You keep it P maybe. You keep it P as it is. Now it will be like 100 CK, P to the power K, and 1 minus P to the power 100 minus K. Okay. Plus summation K is equal to 61 to 100, 100 CK, P to the power K, and 1 minus P to the power 100 minus K.
Actually, sir. Sir, for alpha, what would be the statement? Like it would be reject H naught if H is false, right? For alpha.
Alpha is we reject H naught when H naught is true.
Sir, H A. Okay, H naught when H naught is true. Okay, thank you.
Yeah. So now from here, I guess, see, you can leave it here, or as these are 100 samples in the lecture, I guess sir has normalized. So he has converted this X to he has taken X and he normalized the X. normalization means he converted this x to approximately converted to normal. So what is the mean? How do we convert? So by taking the mean and variance.
Yes.
What is the mean of this binomial?
NP.
So it is 100p.
Yes.
और रजनीगंधा खाइएगा?
So what is variance of x?
NPQ.
100p 1 minus p.
Yes, sir, that is NPQ. 100p 1 minus p.
100p 1 minus p.
Yes.
So if this is the expectation and this is the variance, so I can actually take x very much approximate to normal with mean 100p and variance 100p times 1 minus p.
Right, yeah.
Okay. So sir has normalized it because we know the values of standard normal. So probabilities of standard normal we can actually compute. So if you do so, what will we get? So this is nothing but it's like probability that x is less than 40. Correct? So this is what it is, and when x is when x is greater than 60, probability of x taking greater than 60. Am I correct?
Yeah.
So it's like, see, when are we going to reject h naught? When x falls either less than 40 or greater than 60. Correct?
Yes, sir.
So you can see here, when my x is in between 0 to 39 and from 61 to 100, if my x value is any of these things, then I am going to reject h naught. So that means this particular probability of rejecting h naught is actually probability of x taking values less than 40 plus probability of x taking values greater than 60. So from now on, can you convert this to normal? How can I convert random variable x to normal?
Normal 0 1, sir.
When x is something, some distribution.
Yeah. So x minus mu divided by sigma.
Yeah, x minus expected value of x
divided by sigma of x.
Root
Yeah,
over
or square root of variance of x. Yes,
yeah.
correct.
Will follow normal.
0 1.
Correct. So what can we do? P x minus 100p divided by something like root over 100p times 1 minus p. See, this is just the computation to get the value of 1 minus beta. That's it.
Yes, yes.
We are not doing any new thing. So this is something like 40 minus 100p divided by square root 100p times 1 minus p. So the same thing you get here also, x minus 100p divided by something like that. So now
in both cases, numerator will remain the same.
In both cases?
Numerator will remain the same, that is a complement.
Can you scroll a bit, sir? I wanted to write down this binomial as on their top. Yeah.
So is doing normalization is like necessary?
Not necessary. It actually approximates your probabilities. See, it is very difficult to compute using this binomial summation, right? So you have to add something like some 80, almost 80 values, something like 78 values you should add. So it will be somewhat difficult to add all those, computing each and every value and adding all the 78 values is quite handy. What you should sit and solve. Okay, it takes days to solve it. So in order to, instead of doing that, you can actually approximate the probabilities. Approximately you can find the power. So we don't require the exact power. So even the approximation is sufficient. Okay. So that is why we normalize it. Normalize it, we have the standard tables, right? So that helps us to calculate the probabilities directly.
So for the binomial one, so the parameter is 100 and p, like how does it translate to, this may be a very basic doubt. So
mean and variance, na?
There is mean and variance. So the binomial gives us the mean, right?
Binomial mean is 100p, right? NP. So binomial NP, mean is n times p.
So, but these parameters are alpha and beta, is it? Like 100 and...
There is alpha and beta. See, alpha and beta are significance level and power. They are not the parameters.
No, so sorry, not that. I'm talking about this 100 and P.
Hmm.
So I mean, from binomial to normal. So the expectation, the mean, I will make the product of this 100 and P, and variance 100P into 1 minus P. But this 100 and P, what they have called as that separately, like looking at only from binomial perspective, like only as binomial, is just a parameter. 100 and P to be taken as just a parameters of binomial
100 times
mu.
No, I mean mu will be anyway be expectation of x, right?
Yeah.
No, I'm talking about, sir. I got the expectation of x and variance x from binomial, but from binomial, I mean, looking at only this part, the binomial part, 100 and P.
This
thing. So, yes, sir, only the 100 and P. So 100 and P.
See, this is the probability
100
of
trials.
This is the number of trials you do, and this is the probability of success for each trial.
Each trial. Okay.
Yeah. Okay. Let's proceed. So this thing we know, this is a standard normal Z. So probability of Z less than something like 40 minus 100p by root over 100p times 1 minus.
Sir, sir, can you scroll up a bit for a moment and stay there just for a moment? Like I'll take a snapshot and then I'll.
Okay.
Sir will be providing this document.
Yeah, anyway, I will provide this document after this class. Okay, so this is something like we got power as, so this is probability fz of something like you will get 40 minus some 100p. So you can simplify it further. Like this plus something like fz of 60 minus 100p. So it's not 1 minus, it will be, you will get something like 1 minus, because this is x greater than 60. So I can write 1 minus probability of x less than 60. Then this particular thing, if you standard normalize it, it will be like fz of 60 minus 100p divided by root over something 100p times 1 minus p.
Right.
Okay. So this will be. So usually if your alternative is something like, if you don't know the probability, or if it is not actually defining your distribution, something like here we have p not equal to 0.5, that's it. We don't have a specific value in the alternative. So it's difficult to compute. So you take randomly one value, you make it simple, and you take 0.6 or 0.7, and you just put it here. You just get the values of alpha and beta. Okay, but this is what the computation we do. This is how we find size and power of any test. All right. Okay, let's quickly do these things also, and we will move forward. So now I have a setup of where my distribution is normal mu with variance 1, and my samples are coming from that distribution. And I have I am saying that mu is minus 1, but some of you said that no, mu is 1. So now we are doing an hypothesis testing in order to check which one is true, which one to accept, whether to accept my claim or whether to reject my claim. So that is what we are going to do. And the test is, if x is greater than some c, and again the c is something, some constant, some real constant, and if my x is greater than c, I am going to reject h0. Okay, so this is my setup. We are interested to find the values of alpha and 1 minus beta, which are significance level and the power. So how do we proceed? How do we proceed?
You can make the graph.
Okay, I can make the graph. So what is the acceptance set first?
If it is less than c, it is less than c. If t is less than equal to c. Yes.
This is my acceptance set.
Yes, less than equal to c.
Correct. So now I know the acceptance region. So if x is coming from normal, So that means it can come from minus infinity to plus infinity. Okay, any value. Among these things, so if this is C, what is my acceptance region?
Left side of the C.
Left side
Less
of,
than equal to C. Yes.
so this is the acceptance region and this is the rejection region. Okay.
Yes.
Now we are pretty much interested to see within two values, either mu is -1 or +1. And we know the normal graphs, right? If mu is, let's say mu is -1. So I will draw separately. So if mu is -1, my normal graph is somewhat it will be like this. So mean at -1. Correct? This is how my graph looks like somewhat.
From minus
Yes, sir.
infinity to C.
What is from minus infinity to C?
This graph will go from minus infinity to C, right?
Graph is always from
Minus infinity to plus infinity.
Yes, yes. Graph is always from minus to plus.
So
Mu is -1, so the
yeah,
top will be at minus, the maximum will be at -1.
yes, correct. You know the normal graph, right?
Never touches it.
Now, yeah, somewhere, so C is somewhere here or maybe left side of it also, but let's say somewhere here. So if C is somewhere here, now I know this is the rejection region, because if my X is greater than C, I'm going to reject. And this is my acceptance region. Correct?
Yes, sir.
And similarly, I can have one more graph. More or less, it will be the same graph. So let's say this is one. And my C is somewhere here. So the right side I will reject. And the left side I will accept. Okay. So identifying the regions is a good thing. So you can identify the regions, then the computation is easier. Even if you don't identify and you directly solve, it's okay, fine. So this is nothing but probability of reject H0 where H0 is true. Okay. When will I reject H0? When X is greater than C. Correct?
Yes.
And H0 is true means mu is -1. So now what it is? So mu is -1 means this X becomes normal -1 comma 1. Correct? What is mean? -1. Sigma is 1. So probability of
X minus -1.
X minus of -1
Yes.
divided by 1.
1.
Greater than C minus of -1 divided by 1. So what is this? This is standard Z.
X plus 1. Yeah.
Greater than C plus 1.
One.
So what is this? This will be like 1 minus probability of
Fz
Z
of
less than or equal to C plus 1.
yes.
So this is 1 minus Fz of C plus
C
1.
plus 1. Right.
Now you see you have alpha is equal to 1 minus of Fz of C plus 1.
Okay.
So depending upon alpha value, you can find the value of C. Because we know the standard normal table. So you know the values of these. So once you have some value for alpha, you will get Fz of C plus 1 as something like maybe 0.95, 0.9.
But sir, I don't know C, na, sir.
Yeah, you don't know C. We will know C when you fix alpha.
No, say for example, I took alpha 0.05, 0.05.
Huh?
I took alpha as 0.05, 0.05.
Okay, if you took alpha as 0.05.
Okay, got it, sir.
Got
So
it.
FZ C plus 1 will become 0.95.
0.95.
Yes,
so
yes, got
you
it.
have a standard table, right?
Yes, yes. I'm sorry, sir.
Yeah. From there you can. What we do is we fix alpha to find value of C.
Yes.
Okay. Similarly, you can find the value.
To find C, sir.
So that is what fix alpha. Fix some alpha
No,
value.
no, no, sir has derived like something like F inverse of G and took C outside. I did not get that point.
That inverse will come later on. Here inverse will not come into picture.
So it's like, see, what he did is maybe something like fz of C plus 1 is equals to 1 minus alpha. And this is like C plus 1 is equals to fz inverse of 1 minus alpha.
Okay.
And C is minus 1 plus fz inverse of 1 minus alpha. So you take alpha value,
Okay.
fix one alpha
Got it,
value, you will get the value of C. Okay. Yeah, similarly, we can find 1 minus beta also. Correct. Probability of you reject H naught. When alternative is true. Alternative is true means mu is 1. So you compute it and you can get some value. Okay. But this is how you compute. You compute power and size of a test. Okay.
Can I ask a question here? When you said initially you wrote it as X is greater than C. And then you subtracted the mean from either side and divided by the variance.
Standard. Yeah.
Sorry, not the variance, standard deviation. So that's the standard z-score formula, and that is what you did in the earlier problem also. Is that correct?
Earlier problem also. Yeah. Any distribution, any random variable, if it has mean mu and standard deviation as sigma, so X follows any distribution with mean mu and standard deviation sigma, then X minus mu by sigma follows standard normal 0.
Okay. Yes, just give me one more question I have. Let me complete it. So that's exactly what you did in the previous problem also.
Yeah, correct. That is what we
There was a root there, I thought, when you
No, that
written
is
that.
not rule. You can prove it. Like if you have more, any distribution can be approximated to normal. First thing.
Okay, basically the root is come because standard deviation is NPQ and variance is NPQ and okay. Sorry, that was all. Thank you.
Okay, now
one more person was asking a question. Yash, I think you wanted to ask a question. So
Yeah. Yes. Yes, are you there? Okay, fine. So if you are there, you can ask, but okay, I will just proceed meanwhile. So now this is a good setup. So I have some 100 samples coming from IID normal mu1, and the same I say that mean is -1, but you argue that mean is 1. So it's like you versus me. So I have kept I just wanted to verify whether my claim is correct or not. I kept that H naught null hypothesis as mu is equals to -1 and alternative as mu is equals to 1. But you see here, I have defined a new thing called T. So this is what we actually in the start of the lecture also I have said. This is called as test statistic. So it's a static value you are going to get when you look at the samples, and if you sum the samples and divide it by 100, it's actually the mean of the sample. Correct? So this is the mean of the sample. Am I correct?
Yes, sir.
Yes, sir.
Yes, sir.
So that is what. So this particular mean of this sample, when I look at the 100 samples, this will give me a value, a static value, a fixed value, right? So depending upon this fixed value, I am going to test it. So what I will do is I will reject H naught if my test statistic is greater than some C. So I'm going to find that C by taking alpha and beta. Okay, for some C, if my T is greater than C, I am going to reject H naught. So what is the acceptance set now?
T is less than or equal to C, sir.
Yes.
T
Less than or
when
equal
T
to C.
is less than or equal to C, I will accept my null. Correct. So the acceptance set is this. So you can actually draw on the line and you can see if this is C, this is the acceptance region. So I will accept H naught here, and this is the region where I reject H naught. Okay. So now we have to compute alpha. So what is the probability that you reject H naught given null is true? So that means probability of A complement, which is A complement is nothing but T less than or equals to C given mu is equals to -1. So null is true. If null is true, mu is given to be -1. So now the same thing. Now T is a random variable. Correct?
But T should be greater than C, na, sir? Reject A complement, no?
Yeah, correct. So reject H naught. When we will reject H naught, thanks. So reject H naught. If T is greater than C, we are going to reject H naught.
Yes.
Now what is T? So what is the distribution of T?
Normal.
Uniform.
Normal.
So
Can
X
No,
is,
Sir, can you scroll up a bit?
well,
sir,
mu
for-
and sigma.
Yes.
are you going to take screenshots? If you are going to take screenshots, anyway, I will share this. Okay.
Sir, these notes, I was just looking at that, sir. I want to write it down, but
Okay.
because it's not available, right, in document.
I will upload it. That is what I am saying. I will upload this particular document which I am writing. I will upload it on the phone.
It will be there in YouTube also.
Don't worry, sir. We'll upload just now. Start the session.
Okay. If X is following normal mu1, what is the distribution of T? You should tell these things.
Mu and 1 by sigma square by n. So 1 by n. That is 1 by 100.
So it's normal. Correct. Mu
Sigma square by n.
1 by 100. Correct. Now, if I wanted to convert this to standard normal, what should I do? T minus mu
Square root of 1 by 100.
correct? This is normal 0, 1.
Yes, sir.
So that is what we are going to do. So probability that T greater than C when mu is -1 now. So probability of T minus of -1. So take mu as -1. Minus of -1 divided by 1 by 10. So root over 1 by 100 is 1 by 10. Is greater than C minus of -1 divided by 1 by 10. So what this will be? Probability of, so this is Z. So this is Z. Z greater than C plus 1 by 10. So if I simplify this, I will get probability that Z is greater than 10 times
into C plus 1.
And what is this? 1 minus Fz of 10 times C plus 1. Correct? Hello?
Yes, sir.
Correct?
Yes, sir.
Okay. Just a second. Sorry, my question. If we solve hypothesis testing, we needed Z table. I'm sure in portal they give one value, not the whole table forever. Yeah, see, whatever the values that are required to solve the problem, those values we will give you in the exam also. Okay, yes, this is for you. Okay, yeah. So this is alpha. So this, you fix alpha, we can find C. The same thing, same thing what we are. See, each and every problem, whatever we did till now, we have followed the same approach. So first we have written down the acceptance set, then we have seen the region, acceptance region, then we found out the alpha. So for finding out alpha, so you have to understand what is the rejection region is. So that is what we have taken, and we convert this particular random variable to standard normal in order to, so as we know the probabilities of standard normal, so we convert this particular random variable to standard normal, and after converting we write it in the FZ. So these values we know. So once you fix alpha, we can find the value of C. Similarly, you can find the power also. So 1 minus beta, what is 1 minus beta? Probability of you reject H naught given HA is true. So what is this probability of, again T greater than C given mu is 1 this time. So only one value will. So baki calculation and everything is same.
C minus 1 in place of C plus 1 it will be C minus 1.
That's it.
Sir,
okay. Yeah.
A question. I'm sorry, I didn't get that part. What you did with the test statistic?
Thank you.
Following a normal distribution, mu 1 by 100. How did that happen? Yeah, this part.
This part. Yeah. So if T follows normal mu by 100, mu comma 1 by 100, this is okay.
No. I wanted to know how we came from X normal mu 1 to T normal mu 1 by 100.
Oh, you want to know this thing only?
Yes.
Okay. If X is normal mu 1, so what is the expected value of T?
X minus mu by sigma.
What is the expected value of T?
It's mu by 100. Sorry, no, not mu by 100. 1 by 100 into X plus the value of X is till 100. Yeah.
This is what it is. See, this is actually the mean, right? T is actually the mean. T is nothing but X bar. So what is the expected value of sample mean?
Population mean.
It's mu.
Population mean.
Population mean?
Yeah, it's mu.
What is it? It is mu?
Yeah.
And this is a linear combination of normals. And we know that linear combination of normal is normal. Do you know this?
Yeah.
Everyone?
Yes, sir.
Chakraborty. Hello?
Sorry, sir. I was just trying to write down things. Yeah.
So you know a linear combination of normal is normal?
Yeah, kind of like now that you said it kind of like
okay, now that I said you are okay with that.
Yeah, I mean there are gaps in my education, sir. I'm so sorry.
Okay. So in week 7, I guess, in week 7 or week 8, not week 8, in week 7 only, I guess. So there we have proved this actually. The linear combination of normals is actually normal. Okay. So this T or the sample mean is nothing but the linear combination of normals, where X1 and X standard are normal samples. So you can find the mean of this new random variable T and also the variance of this T. So when I compute variance of T, it will be something like X100 divided by 100, and this is something like 1 by 100 square of 100 times variance of X. So this is something like variance of X divided by 100. So variance of X is 1. So the variance of T will be 1 by 100. So the mean is mu and the variance is 1 by 100, and I know that this follows normal. So therefore T will be normal mu comma 1 by 100. Now okay?
Yeah, got it, sir. Thank you so much.
So from here to here, you know, right? So if I have any random variable, just subtract mean and divide it by standard deviation, then that will follow standard normal 0. Okay. Okay.
So when we are writing it as given mu is equal to -1, that is what is the value I'm assuming in the mu.
Value for mu.
Okay. Okay.
Yeah. Let's come and deal with some types of hypothesis testing. So one is called simple hypothesis and other is called composite hypothesis. And simple hypothesis is nothing but a hypothesis that completely specifies the distribution of the samples. Like if I know the probability of heads is 0.5, so I can completely look at the distribution of the samples, right? I can take the probability of heads as 0.5 and I know that the probability of success is 0.5 now. Now whatever the parameter is there, that I have given some specific value, and when I given some specific value, so I can see the distribution of that particular sample. Okay. If you don't understand whatever I said till now, simple hypothesis is nothing but it will be like equal to. Okay. So even if you understand this is okay. And whatever are the 2 or 3 statements I said, whole collectively is what it is. So a simple hypothesis examples will be like this. So where the something like null is like probability of heads is 0.5 and alternative is probability of heads is 0.7. So this is something called as simple null versus simple alternative. So why it is simple? Because there is an equal to symbol. So that means this particular hypothesis will give me the distribution of the samples completely. Okay. So there is another example also like this. So this is also simple null versus simple alternative. And the simple null versus simple alternative is not that common, is not commonly seen. So very rarely we take both the null and alternative as simple. And what composite is, the other part is, it does not completely specify the distribution, wherein you see in the alternative, you see probability of heads is not equal to 0.5, that's it. You don't know what is the probability of heads. The parameter remains parameter only. You don't know the parameter value. Once you don't know the parameter value, you cannot specify the distribution of that completely. Correct? Or if you don't know, if you didn't understand this, you simply, if there is no equal to sign, if there is not equal to or greater than or less than or equal to, greater than or equal to, this will correspond to composite hypothesis. Okay. Hello.
Yes, sir.
Yes, sir. Okay.
Okay.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Simple hypothesis. And other than equal to is composite hypothesis. And we are not interested to say it directly like this. So we will bring up these technical terms and everything. We define it properly. So here you see, we have simple null. So this is a simple hypothesis because probability of heads is equal to 0.5 versus composite alternative. And this is very commonly seen. So either it is probability of heads not equal to 0.5 or probability of head greater than 0.5 or probability of head less than 0.5. These all are composite alternative, composite hypothesis. Okay. So even this is also one more example. So this is probability of head is greater than 0.5 and probability of head is less than or equal to 0.5. Null is this and alternative is this. So this is something like composite null versus composite alternative. So even this is also not very commonly seen. And there is one more example, which are samples coming from normal mu1. So this is also something falls under simple null versus composite alternative. Everyone getting sleepy or what?
No, sir.
No, sir.
No, sir.
Yes.
No,
sir.
No, sir.
Simple versus composite it is.
Okay. So now these are types of hypothesis, and there are some standard tests. So these are the tests we are going to do throughout week 11. So whatever the rest of the lectures you are going to do, either one of these tests only. Okay, it falls under one of these tests. There is no new test. These are the tests we are going to do. So I will explain one by one. So first thing is, if you have only one sample means if you have only one distribution. So that is what professor intention is also. So if our samples are coming from one distribution. So something like this. So x1, x2, xn coming from some IID x, where expected value of x is mu and variance of x is sigma square. Our first standard test is testing for mean. So mean of this distribution. So that is the first and foremost test we do. We test for mean. So when I test for mean, my test statistic will be
Plus x2.
So this will be the test statistic.
Right.
Okay. And I am going to test for mean. And there are few categories where null and alternative can be defined. So one case is, this is case 1, where my null hypothesis is mu is equals to c. And also one more thing, in this particular course, so in stats 2, our null will always be simple. Okay. So we are not going to deal with the problems which are composite null. So our null, in our null, it will always be equal to only. So this is the case 1 where mu is equal to c, and alternative may be like mu is greater than c. So this particular thing has a name. What is that name?
Which one, sir?
Composite alternative.
This is a composite alternative. When mu is greater than c is in my alternative.
Okay, right tail.
Correct. So this
right tail
is right tail test.
Yes.
Okay, there. So you see, if your mu is greater than c is in my alternative, what I am going to do is I am going to reject on the right.
If it is on the right hand side.
So if it is on the right hand side, I am going to reject my null. If it is on the left hand side, I am going to accept null. So this is called right tail test. But if my alternative is mu less than c, then you can easily guess the name. It is left tail test. And if it is not equal,
two tail.
So we say it's a two tail test. These are just the names of the test.
Yes.
Okay. So depending upon the alternative hypothesis, we name these tests: right tail, left tail, and two tail. And this is for testing for mean. Okay. This is first only one distribution. Samples are coming from one distribution, and we are testing for mean is one test. And the other test is
Sir, before that, the right tail, left tail, and two tail. It will be either greater than C and less than C. But what do you mean by not equal to C? Not equal to C might fit in any one of the greater than, less than C.
Yeah, any of the greater than or less than.
And what is the point of giving another name for one of the previous two?
Because you will check on both sides. No?
See, that is the name given. You can name it like right and tail test, right and left tail test.
So I can still call this first one as a two tail and the second one is also as a two tail because they are not equal to C.
See, this was named as a right tail because you are going to reject your null when it is on the right side of it, right side of some critical value. Okay.
Yeah, I could see that one, but I could not really make up my mind to the third case. Because third case, it always be one of the two, previous two.
Not always the one of the two. It's actually the combination of those two. see here itself I will tell you, if you are something like, okay, I'll tell you very simply. If your mu, whatever the test statistic value is actually less than C also, you are going to accept null.
Right.
Okay.
Right.
And here, if your mu is greater than some C, or your test statistic value is greater than some critical value, you are going to accept null. But that is not the same case here. Here, your test statistic should be very much close, or we will define based on the test, we are going to define
one range.
Yeah, some range. If this is C, some range, or maybe sometimes the range is very small. And if your mu is other than this, here you will reject, and also here you will reject. So this is the region, rejection region.
So just now we discussed the 40-60 case, that number of toss.
Yeah. So that is a two-tailed one.
Yes, that is a two-tailed test.
So two-tail matlab either the left side or the right side you go, we are going to reject.
Two-tail means rejection on two sides.
Two sides. You are going to reject on the two sides.
Right tail means rejection on right side, and left tail means rejection on left side.
Correct.
Okay.
Okay. Yeah. So that is testing for mean, and there is another standard testing for variance. So if it is for variance, it will be somewhat when H0 null as sigma is equals to C, and alternative may be like sigma greater than C and sigma not equal to C, or sigma less.
All three cases will be applicable here.
Yeah.
Also.
So that is testing for variance. For variance, we are going to test. So it will be sigma now. It's not mu. Okay. Yeah. This is for only one distribution. If the samples are coming from one distribution, two testings are there: testing for mean, testing for variance. What if the sample? There are two samples or samples coming from two distributions. Something like this. So the setup is like this. So there are n samples coming from IIDX, and there are n more other samples coming from IIDY. So each of the distribution has some mean mu1 and variance sigma 1 square, and for y it is like mu2 and sigma 2 square. So now we have two means. The testing we do here is testing to compare means. So when we have two samples, we compare those two means. So my null will be like mu1 is equals to mu2, and my alternative is like mu1 not equal to mu2. Okay. And this is one kind of testing we do.
There is no role of C here.
There is no role of C here. So either you are comparing the means. So which one? Either the two means are equal. So for example, you see there are two classrooms, and you wanted to look average at the marks. Mean average marks. Okay. So one class you choose randomly 10 people, and another class you choose randomly 10 people, and you compute the average. And you just wanted to compare those averages. So which class is better? So which class has a better students, like this. If you want to compare, that is what we do here. So you take two different samples from two different distributions, and we are going to compare their means. So if the two means are equal, we will conclude something. If the two means are not equal, then we are going to conclude another thing. So that is the testing we are going to do. So this is also one standard test we are going to do. And the final one is testing to compare variances. So when I say variances, what should be my null?
Both of them are equal, sigma 1 equal to sigma 2.
Yeah. So variance of x is sigma 1 square and variance of y is sigma 2 square. So something like sigma 1 square is equal to sigma 2 square, or I can simply take
sigma 1 sigma 2.
Sigma 2. And the alternative I take it like sigma 1 not equals to sigma 2.
Correct.
Okay.
Yes, sir.
So this is about, these are the standard tests we are going to do. So there are 4 standard tests we are going to do.
So there can be more than 2 samples also, right?
There can be more than 2 samples also, but we are not going to worry about that thing in this particular course. So these are the standard tests we are going to do.
Will there be more courses on stats in subsequent courses like in diploma and diploma 2?
I don't think, but as this got converted to BS, maybe we should bring up one particular course of stats into. somewhere in 4th year or somewhere as a major. Okay.
Sir, hello.
After 3 years. Yes.
Yeah.
So in this two sample tests, how we are going to calculate the parameters like alpha and beta?
So alpha and beta, so that we will see na how are we going to do and what are we going to do. Okay. Okay. So this is about 10.3 and 10.4 is basically sir has discussed few
that motivational, yeah.
It's just the motivation. So he has given some situations.
Yes.
And he has given some null and alternative. How do we fix null and alternative?
3 cases he has quoted, yes. 3 or
So
4
you just
cases.
go there and you can just watch the lecture.
Yes,
Watching the lecture itself is sufficient. So
yeah,
there are no problems to solve in that.
More of a theoretical kind of thing.
Yeah, more of a theoretical kind, and he actually gave some good examples.
Yes, sir. The examples are really good.
Yeah. So just go there and you just watch, and I will just conclude with how to get the p-values and what is p-value, what is critical value, and how. So when a question is given to us, how do we compute or how do we solve for
Yes, sir. Because today is
critical value and
6, 7, 8 or more.
yes, sir. Because today is also the extra activity submission last date.
So which lecture are you talking about, sir?
I'm talking about now 10.5. So
10 point or 11, sir? Are we doing 10 or 11 here?
Sorry. 10, 11.4 and 11.5.
Okay, sir.
Okay. So someone mentioning extra activity deadline or something.
Yeah, today I think 15 or 20 minutes left.
So when are you going to do that then?
Huh?
When are you going to do that?
Actually, I'm almost done, sir.
Don't bring that topic here. Please continue.
Okay, you do that, but I will do some two parts. So maybe I will start with how do we do this jet test or the first test we have, right? So I will write the setup. So this is Z test. This is lecture 10.5. Okay. So how do we do this Z test? So when we have some samples x1 to xn coming from some IID normal mu some sigma square, let me take something like 3 square, and yeah, so these are some n samples coming from this normal mu 3 square, and later what we do is we have to define a test statistic. So we are trying to test for mean. This is the testing for mean case. So this is the first standard case we just discussed. So we are trying to test for mean, testing for mean. So when I am testing for mean, what should be my test statistic? So I define a test statistic.
x1 plus x2 plus x3.
So which is sample mean.
Yes. x1 plus x2 plus x3.
Xn divided by n. Correct.
Yes.
And what is my null?
Null will be equal to mu, no?
Mu equals to some c.
Yes.
And alternative is mu is greater than c or some. So let's take the lecture thing only. So sir has used null. So mean is equal to 0 or mean is greater than 0. Alternative. So the test is we are going to reject H0 if my test statistic is greater than some c. So in order not to confuse a lot, so whatever the alternative sign you have, okay. So look at the alternative
greater than,
and whichever the alternative sign is there, that will be the test sign also.
Okay.
So if it is greater, it will be greater. If it is less, it will be less here.
Yes.
If it is not equal, then it will be a range here.
Yes.
Okay. So
my alternate will tell me that is a right tail or left tail or
Your alternate will tell you. So what is the test? Your alternate will tell you. and you are going to reject H naught if this particular test statistic is greater than C. And now we are interested to find the value of C. Let me tell my alpha. I'm going to fix alpha. I can only tolerate 5%. That means alpha is 0.05. Okay. So now let's compute alpha. Now let's compute C. Now let's try to compute C. So what is alpha? Alpha is probability of reject H naught given H naught is true. Probability of rejecting H naught. When we will reject H naught? When T is greater than C. Correct? And H naught is true means U is equals to 2. 0, sorry. If someone feeling really bored, it is actually being it is actually being YouTube stream. You can watch it later. You can take rest. Okay.
That's fine. We can continue.
It is not about boring. It's just that it is a little demanding. Let me put it as on the logic part. Can you, if you don't mind, yeah. Okay.
Yes, sir. And we can kindly go a little slower. First time looking at these things.
Okay. So, okay, I will do one more thing then. So today we will do this thing. We will try to understand this thing. Maybe on Wednesday I will take again in one hour, maybe from 10 to 11 or something. So we will do in parts. Will that be okay?
If you are going to do it, then it will be
Yes,
okay.
yes, sir. Surely.
Yes. Today we can complete 5, 6, sir, and then 7, 8 on that day we can complete.
No. See, I can see that many of you are like getting this. See, continuously there is a theory.
Yes.
So no student can listen or concentrate more than 50 minutes.
Okay.
Have you heard about this?
Yeah, it's kind of a dry.
Yeah. So after
Pomodoro.
Huh?
Sometimes Pomodoro जैसे करके बोलते हैं इसको.
Yeah. See, that is why in the colleges or big institutions, no class will be more than 50 minutes. So some scientists have proven that how much ever concentration you put on one thing, not only studying. So you think like maybe some cleaning your room itself. So how much you can only continuously spend 50 minutes on it. In the 51st minute, you will definitely, your mind will not make you to do it. It will ask for rest.
It will apply to the whole course too, sir.
Every course it will apply to.
Sorry.
Means that is this course doable in 4 months? It will apply to that thing also.
Yeah. So that
But
is why
all your teaching materials are going to be uploaded.
see this thing I will upload.
Now even the forthcoming one, the one what you're talking about on Wednesday.
That one also I will upload. That one also I will upload.
Okay.
Everything I will upload.
Yeah, it sounds that it is a little bit in overdose at the same time.
Yeah,
so
correct.
We need to rerun a couple of times to
get that. Correct. So now what you do is you just go back and watch till 10.4 and watch 10.5 also. I will just complete 10.5 now, and 10.6 we will do it in the next.
It's 11.6.
Sorry. Why I am getting 10.
I think you yourself got into trap, I think.
No. 6 to 8 I have taken math session and it was on week 10.
Yeah.
So I was in that week 10 itself. So I am getting 10.
Sir, in 7 and 8, sir, 11.7 and 8, professor has solved, I think, at least 6 to 7 problems, right?
Yeah.
So some clarifications are needed, like how he is taking inverse, because he is doing calculation very fast. He is saying that, I am jumping.
Okay. We will do that thing in on Wednesday. Okay.
Okay.
So I will just complete. 10.5 is very small.
Yes, sir. That's very small. Yes, sir.
So I will just complete it. Just try to focus, or if you are unable to focus, just see what I am writing.
No, we can continue, sir.
Okay.
I think Wednesday is a submission day.
Wednesday not
थोड़ा जल्दी कर लेंगे दोपहर में.
We can do submission before 10.
That's for week 10. Submission
Yeah,
is
that's
not.
for week 10. That's for week 10. We have already got so many time.
So you can submit it early, right?
Yes.
You should make time. I am ready to make time, so you should also make.
Yes, sir. Yes, sir. Yes, sir.
We'll do that, sir.
Okay. Okay. So I will just finish it here. So what are we doing is, this is just the setup. Until here, this is the setup. So I am taking samples from normal mu 3 square. Some variance I know, but I don't know the mean. When I don't know the mean, I don't know the distribution. But my prediction is, yeah, the mean I know, the mean is 0. And I know the distribution, this follows normal 0, 3 square. But you suspect me and say, no, I have seen the samples and I think I have taken some random samples and I think mu is not 0. It is actually greater than 0. It is not 0. It is actually greater than 0. That is what your claim is. You are suspecting me and you took one claim and you are trying to be like either yours is correct or mine is correct. That is what we are going to do. So for that, what we do is we randomly pick some samples out of this normal mu 3 square. Okay. So those are these samples, x1, xn, x2, x3 and so on, xn are the samples. And this particular t is what it is testing. We should do testing, right? How will, for anything to conclude, we should actually test it, and depending upon the results, we actually conclude something. So for the testing thing, we need some static value. So which one we will compare? Which one to compare? So some values to compare. So that value, that static value will be coming from this test statistic. So this particular test statistic we will define. So this is all our setup. So we will define this test statistic. I have taken it as sample mean because we are testing for mean. Okay. If I am testing for variance, I should have taken something like t is equals to some variance formula.
Yes.
Okay. If I am testing for sum, so we have seen the above problem also. We have seen the number of heads. So that is the sum of all the random variables. So for that, I have taken the test statistic as sum only. So whatever I am testing, I will take the test statistic as that thing only. So that thing I have taken. So now I have seen some n samples so that I know the value of mean also with me. And what I will do, this is my test. I will reject H0. I will reject H0 means I say you said a bullshit thing and I don't like that. Mu is not 0. Mu is actually greater than 0. You will say mu is actually greater than 0. If your test statistic is greater than C. So this is the setup. This is the test, null. So null and alternative. These all are the setup. This is test statistic. Okay. Now what we do is we actually try to find this C. Okay, we are interested to find that particular C. So for what value of C I can actually reject H0. So which one is the better C? So that is what we are going to do. For that we need this size and power. So we know alpha is probability that reject H0 when H0 is true. And when are we going to reject H0? Here test itself says that you reject H0 if T is greater than C. So probability that T is greater than C when H0 is true, matlab H0, when will H0 be true? Mu is equals to 0. So that is what it is. T greater than C, mu is equals to 0. So now T, I know T is actually the sample mean. So if X is coming from normal mu 3 square, what is the distribution of X bar, which is actually T?
Mu divided by mu
1 by
comma
3 square by
sample
n.
size, yes.
Yeah, 3 square by n.
Yes.
right? So
Yes.
when t is this, t minus mu by root over 3 square by n follows standard normal.
Yes, 0, 1.
So the same thing we do. So t minus, what is mu value? H naught is true. So you
0.
just substitute the mu value t minus 0
0.
divided by root over 3 square by n. So in the lecture, is it 3 or 4? Lecture it is 4, I guess. So okay, I am taking this 4 because I know the values. Sir has given the values, or else I have to compute the values. So this is t minus 0.
Correct here also, sir, on the right hand side, 4 square and 4.
Yeah, 4 square, 4 square, and
4
4
square.
square. So this is greater than c minus 0 divided by root over 4 square by n. So everyone getting how am I doing this?
Yes, sir.
Yes.
So, but why we are subtracting 0? It should be mu, na?
Mu, but we said
Mu is 0.
mu is
Null hypothesis is mu
null,
equal to
null
0.
is true,
Okay,
right?
okay, okay. We are
Null is
subtracting.
true.
Okay.
Yes, yes.
Right,
Null
right,
is-
right.
So that is what. So this is standard normal now. So this will be like z greater
G.
than some
G.
root nc divided by 4. So just I have simplified this.
Yes, yes.
Okay. So now this is something like 1 minus probability of z less than or equal to root n c divided by 4. So this is something like 1 minus fz of root n c divided by 4. Correct?
Yes, sir.
Yeah. So from here onwards, what we do is we fix alpha. As I said, you can take any value for alpha. Like whatever the tolerance you can tolerate, you can take that much error. So there are some values, specific values. See, you can simply see. So when my c is 0, what happens? When my c is 0, alpha is 1 minus fz of
Z of 0.
0. So what is fz of 0? We know very standard.
Half.
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 So it's like, so this is like half of the region.
Yes, yes.
So this is 1 minus half, which is 0.5.
Yes.
If you are okay with 50% of error, if you are okay with significance level of 50%, then my critical value should be 0. Okay. What it says, c value 0 matlab, you reject h naught if the test statistic is greater than 0, test statistic value. So whatever the sample mean you observe from the samples, if it is greater than 0, you reject h naught. So is this a better test?
No, sir.
No, right?
No.
So that means you have a 50% chance of going type 1 error. So similarly, there are few values. If c is something like 1.62, so what will be alpha? 1 minus 1 minus fz of root n times c. So it is like 1.62 into n divided by 4 root n. Okay. So yeah, again, if you fix some n value, something like n is equals to 10. So this will be like 1.62 into root 10. So we know the standard normal table, right? So if you compute this and find the value of fz of that, so you will get something around 0.9. So this value is somewhere around 0.9. So this will, alpha value will be somewhere around 0.5. So there are some values. So depending upon value of c, and 3.91, I guess. So depending upon the value of c, my alpha value is varying. So this is like 0.5, this will be 0.1, this is 0.05, 0.01, and this is 0.05, this is 0.001. So what it tells, so when my critical value is getting bigger and bigger, my type 1 error, probability of happening type 1 error is reducing. So you should observe that thing first.
Yes.
So when C is 3.91 means what you are actually doing is you are going to reject null if your test statistic value is greater than 3.91. Okay, so that means if your mean is greater than 3.91, then only you will reject null. Even if it is 3 or even if it is 2.5, even if it is 1, you are going to accept null. Okay, if you are doing like this, what happens, you know, your beta value will be increased.
Yes. Making type 2 error.
Type 2 error, chance of happening type 2 error will become more. So that is why we don't even go till here also. So these are the commonly taken values for alpha. So usually we prefer alpha to be equal to 0.05 or alpha to be equal to 0.01. So we don't want 0.5% error or 0.1% error. That much accuracy of type 1 error we don't need, because if I go for accuracy for type 1 error, that may lead to the other consequence that type 2 error probability will get increased.
Even for medicines also, new drugs also.
Yeah, that will happen, right? For drugs also, they follow these things. So there will be some error. So that is why for some people it will show adverse effects. Okay, so this is how you see. So what final statement is, by following this Z test at significance level, this is how we pronounce significance level at the rate 0.05. So if significance level I have taken it as 0.05, my test is basically I'm going to reject H0 if T is greater than 2.08. So this is what my C value is at the significance level of 0.05. So that means 95% surely I can trust this test. With 95% surety I can trust this test. So there is a 5% of going error, type 1 error. So that is what this significance level tells me. Okay.
What is this 95%?
What is this?
What is this 95%? You said something 95%.
See, if 5% error is allowed, baki 95% is.
So that is called confidence level or what?
Confidence. Our not the confidence interval.
No, not interval level. Confidence level.
The confidence level. Yeah. So with 95% surety, surely I can tell that this test gives me. So if I perform this test 100 times, 95% of the times it will give me the correct. So if H0 is true, then it will give me, I will accept H0. If null alternative is true, it will give me accept null, accept alternative. So 95% of the chances we will get it correct. And there is a chance of 5 times we go wrong. So that is okay. Yeah. So now you can solve the problems till 10.5, and on Wednesday we will see what actually this p value is, and we will try to solve that 10.7 lecture also.
So 6, 7, 8 we'll discuss on Wednesday.
6, 7, 8 we will discuss on Wednesday.
Okay, sir.
Okay.
What time, sir? Wednesday?
Yeah.
10 o'clock.
At what time, sir?
Yeah, most probably we will. If it is on Wednesday, if you don't have any sessions, we can schedule earlier also, somewhere around 8 p.m. or.
I think on Wednesday we don't have any sessions, sir.
Yes.
Okay,
Sir.
I will.
8 o'clock is fine, sir.
Okay, I will check the schedule and I will.
Yeah.
Same thing I will do. I will add the calendar, add it in the calendar.
On Wednesday we don't have any session.
That will be helpful, sir.
Okay. Okay, I will upload this document now, and on Wednesday document I will upload it after Wednesday session. Okay.
Okay, sir. Thank you,
okay.
sir.
Okay.
Thank you very much.
Yeah, thanks a lot.
Thank you, sir.
Thanks for your patience also.
Thank you,
Thank you for your patience, actually.
We are thankful to you, sir, that you
Actually,
came.
yeah, thanks to you.
You took extra class and helping a lot.
Fine. See, even if I talk a lot, you should listen, right? At least. So for doing that is a good job. See, teaching what I'm actually shouting and I don't get sleepy. So you are sitting there and you should listen for 2 hours is a difficult task.
Sir?
Yeah.
In week 11, whatever maths we have covered, in this hypothesis testing, this much maths is only there, or there are more maths which we are not covering in this course? Or this much maths is only there for hypothesis testing?
This is not there. There is a lot, but we are only dealing this much.
Okay, so more math is there.
So there are different. These are the only 4 or 3 standard tests we discussed. There are many tests.
A professor has also talked about the goodness of fit, something like this.
Goodness of fit, but he also doesn't want to more focus on that thing.
I think that will cover in week 12 or what? Because week
no. See, we are not going to bring that thing. That is actually another big topic. So that goodness of fit is actually fitting. So we have done.
There are so many topics we are leaving. Then when those topics will be covered?
No. These things will be covered in machine learning. Okay? Not all the topics we are leaving. See what happens.
ANOVA, on that day you said that ANOVA we are not covering. Then we are not covering goodness of fit. We are not covering non-parametric hypothesis.
That thing is, if we start, it's not like it's covering. Matlab, you just say hello and you go come back. It will not be like that. If we are starting the topic, it will take to some other topic, and you should, in order to understand that, you should go in deep again.
Yes.
So that will take some 2 or 3 lectures more.
So will it be covered in business analytics? We have a paper on business analytics also.
That I don't know. That I am
okay.
not sure.
Okay.
So what we are going to do is, maybe this particular